All right, here we go. I am going to solve another of the released free response questions from AP Physics 1. This one is the one that I generally refer to as the Bumpy ramp. I remember that when this question actually came out on the AP exam, and of course was released shortly after that, physics teachers everywhere, including myself, were kind of like, wow, haven't seen anything quite like this before. And of course that's true to the spirit of the AP exam often for physics, is there are questions on there that are often designed to be different than anything that you're likely to have seen before. And you just have to accept that and know that that is, in a way, the nature of physics. I mean, problem solving is tackling things that you haven't seen before. So nonetheless, this should be a solvable problem if you're familiar with the core concepts of physics. So let's see how we can do on this. As usual, I suspect that my solution will get the points that would be allotted here. The problem is worth 12 points, but don't consider this to be an official solution. I'm not really checking against the published rubric. So it's possible that I'll miss a point or two perhaps, but it's probable that I'll get the full points. Just to give you that disclaimer. Also, it's probably going to take me more than 25 minutes because I'm not going to just try to solve this problem as a student would or even as a teacher would. But rather I'm going to be trying to explain the physics behind it, trying to give you some deeper insights into how to just approach AP exam questions in general. So I'm definitely not trying to keep myself to that 25-minute time limit. Okay, with that said, let's get to work. So the question involves, at a glance, an inclined plane with a cart on it. That's very familiar looking, but we do have these little, well, bumps. And of course, if you read through the question, I'll just kind of scan through it quickly. Maybe I'll just highlight some key details. So it's a long track. It's inclined at an angle theta, which we can see the diagram, to the horizontal. And it has these small speed bumps on it. Okay, so that's the highly unusual part for a physics kind of question. So the bumps are evenly spaced, a distance of d apart. The diagram shows that nicely, as shown in the figure. The track is actually much longer than is shown, with over 100 bumps. So we're just seeing a section of a much longer track. A cart of mass m, notice that that's an uppercase m. I had mentioned this in a previous video that whenever they present to you a symbol for a quantity, like a cart of mass uppercase m or angle theta over here, it's really important that throughout this problem we're going to stick exactly with their notation for their designated letters, like mass uppercase m. So the cart is released from rest at the top of the track, and the student notices that after reaching the 40th bump, so this is well on its way through the 100 bumps, the cart's average speed between successive bumps no longer increases. So in between the speed bumps, it's essentially like an inclined plane, and in an idealized inclined plane, we would expect a constant acceleration. So if there weren't speed bumps, we'd expect this cart to just go faster, 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 faster. And clearly that's not what's happening here because of these speed bumps. The speed bumps are disrupting it so that on average, the speed between bumps is the same. On average. Okay, so that's going to be an important part of this problem. Okay, just to continue on here. In fact, it reaches a maximum speed of v average. So v average is the average speed that is ultimately reached once this cart has traveled through enough of this track. So they've kind of called out the 40th bump. Let's just think of it as we're well on our way. And we've reached this kind of this pattern, if you will, like the average speed between bumps remains constant from this point forward. And of course, this means that the time interval taken to move from one bump to the next becomes constant, which would be implied if the bumps are evenly spaced and they have the cart has an average speed that's the same each time. Part A says to consider the cart's motion between the 41st and bump 41 and bump 44. And in particular, in the figure below, we are to sketch a graph of the cart's velocity v as a function of time, from the moment it reaches the 41st bump until it reaches the 44th bump, in effect. So that's what our first job to do is. We're going to be directly sketching into this graph what this cart's velocity time graph would be expected to be. Now again, if there were no bumps, okay, let me just kind of sketch this in as not my answer at all here, but if there were no bumps, I would probably just start at some point along this axis. Now remember, this is the 41st bump, so it would have some velocity, non-zero at this point, And if it weren't for the speed bumps, I would just be thinking of a constant acceleration as indicated by a constant slope, something like a single straight line like that. Okay, so that's not what we've got going on here. What we have is, basically think of it this way, between the bumps, we kind of have that idealized inclined plane. This cart is going to be expected to accelerate. However, when it interacts with a bump, there has to be a very dramatic slowdown to, in effect, reset to the condition it was at the previous bump. So I'm just going to sketch this in to kind of show you what I'm thinking of here, and maybe I'll address it a little bit more after that. So let's do something like this. Let's say that it's just come out of this 41st bump here. It's going to have a constant velocity, I'm sorry, I misspoke, a constant acceleration as indicated by a straight line with a positive slope here, until it interacts with that bump. So let me just kind of show you what I'm thinking here. There's going to be a very dramatic slowdown, something maybe like this. So it slows down, and what I'm really thinking that's important here is that the velocity it achieves after interacting with that bump really should be the same as the velocity that it just came out of the previous bump. What's going to happen now is this exact thing is going to repeat over and over. So it finishes interacting with that bump 42. It's basically on the smooth part of the inclined plane, so it accelerates with a nice constant acceleration, ultimately reaching that same speed. In fact, let me just back that up a little bit. I went a little bit too far. I want to go just before that dashed line, so somewhere's around there. And then, of course, it interacts with the speed bump to very dramatically, again, slow down. And repeat. Faster, 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 and then a dramatic slow down, slow down, slow down. And of course, there are more than 44 bumps here, but that's all that we've been asked to do. So something like that. The key features that I want to stress are a constant acceleration, as indicated by a constant positive slope here. It's speeding up. So that is the smooth parts of the ramp, if you will, and the very dramatic interactions with each speed bump, slowing it down, slowing it down, slowing it down. So that's the gist of what I'm thinking of for part 1. Okay, and just to clear back to the starting here, I'll even get rid of these. These were just for me talking. So in effect, I think that's my answer to part 1. And going back, just to make sure I've answered the question for what they've asked me to do so far, that was it. Sketch a graph of the cart's velocity time graph. And of course, they've already set this up as velocity time, so all I had to do was sketch it in. So, moving on to part 2, over the same time interval, so we're going from bump 41 to bump 44, draw a dashed horizontal line at that average speed that it has achieved throughout this motion. And they want us to further label it V average. Now, of course, I wouldn't change colors if I was actually writing this. In fact, when you're writing your EP exams, you're typically restricted to using black and blue pens or pencils. So I'm going to switch colors here just so it stands out in the video here, but realize that that's not something you would really want to do on your AP exam. So the average velocity here, well, let's think of it. This is a velocity time graph, and among other things, I can think that the area underneath it represents the displacement. So between bumps 41 and 42, for example, just to temporarily kind of sketch this in here, between here and here, there's a certain amount of displacement as indicated by that shaded in area. What I need is an average velocity. So I'm going to draw a new graph here, and of course it's going to be a horizontal line because that's what it means to have that, that constant, or at least that averaged velocity. And I need it to have the same area as that red shaded figure that I just showed you here. So what I'm thinking of is it's going to be something basically right down the midpoint, okay? Because especially if you think of it as a constant acceleration, then on average, you are going to have a velocity that is halfway between your two extremes. So if you think of this as the lower velocity and this is the higher velocity, since the acceleration was constant, the average velocity would be right in between. So I'm actually going to just sketch this line in horizontally, going right across there. Of course, you can use a straight edge if you're doing this yourself, or even the edge of your calculator. I'm just kind of freehanding this, so hopefully that is sufficiently clear that that is a straight horizontal line. Don't forget that they told me to to label the line VAVG. And again, let's stick with exactly their notation. Let's not try to change that. So label this V AV G. All right, so that should do for subpart 2. And again, just to notice that displacement, the area under what I've just drawn in here, that displacement would be the same as the actual graph that I started with, the blue graph. In fact, you could think of it as literally taking this little triangle poking above the red line and fitting it in to that space right here. So that's how I'm confident that this line really does represent the average velocity, because the total area of this red line graph would match the total area of the blue sawtooth graph is what one way to describe that shape. Okay, just go back to the way it would be like so. Okay, did I get that? Oh, no, too far. There we go. All right, moving along to part B. Part B says, suppose that the distance between the bumps is increased, but everything else stays the same. Is the maximum speed of the cart now greater than, less than, or the same as it was when the bumps were in their original closer together configuration? So if we jump back to the diagram here, let's imagine that this is reconfigured so that we have a larger, that's kind of messy, we have a larger D value. So if the bumps are spaced further apart, well, there's going to be fewer disruptions, right? It's going to have that smoother incline for a greater distance and therefore a greater time. The acceleration being sustained for longer, it's going to reach a higher velocity, right? A higher end velocity between the bumps, and therefore also a higher average velocity as well. So I think I can go directly back in there. I think I've convinced myself. I sometimes like to kind of do the reasoning if I'm unsure of what I'm going to commit to. But if you're actually feeling pretty confident with it, there's no problem with checking the box and then filling it in. So just make sure I get this right, is the maximum speed of the cart now greater than, less than? It is going to be greater than. And explain your reasoning. I'll try to keep this brief but clear. With the bumps spaced further apart, the cart will have a larger time and distance to accelerate up to higher speeds. And I think that's all it was asking me, right? Is the maximum speed of the cart. So let me single out the maximum speed just to be very, very clear. So up to higher speeds, including the maximum speed achieved just before interacting with each bump. Okay, so that should do the trick. It'll reach higher speeds because the acceleration is disrupted less often. It has more time. It has more distance to accelerate. And of course, think of the extreme. If the bumps were really far apart, like imagine that there was a very long incline and there's only one bump at the top and one bump at the bottom, surely you would agree, I hope, that along that long track down, it would have a very, very long amount of time to accelerate. It would reach a very, very, very high speed before it reaches that bump at the bottom. So yeah, this is pretty good. Moving on, part C. With the bumps returned to their original spacing, okay, so let's keep this straight in our minds because they're kind of changing things on us back and forth. So we're back to the original arrangement as shown in the original diagram. The track is then tilted to a greater, okay, let me just get this in here, a greater ramp angle theta. The question I'm now being asked is the maximum speed of the cart greater than, less than, or the same as when the ramp angle was smaller? So it's kind of a repeat of the part we just did, part B, in that we're trying to figure out what's going to happen to the maximum speed due to a change that occurs. But in part C, to be clear, we are keeping the bumps the same spacing, but we're imagining, and I'll just kind of temporarily draw this in, we're imagining that instead the the plane, the ramp is increased in how steep it is, right? So it's the same ramp. The bumps are equally spaced from before, if you can visualize that. The only change is that it's a greater ramp angle. So with a greater ramp angle, again, I'll just kind of think this through right now. Of course, I know, and of course this is well known if you've covered inclined planes, that the acceleration of a block down a frictionless ramp, and this is well approximated for our cart on wheels here. The cart on wheels effectively is there to reduce or effectively even eliminate friction. So I'm thinking of it as being modeled as if it were frictionless. The cart, of course, will accelerate with a greater acceleration as it gets steeper. In fact, you may be familiar with the equation for that, that the acceleration for an idealized frictionless incline, sliding down it, is actually g sine of theta. So that's something you probably would have come across before if you covered inclined planes, which is a very standard topic here. So between 0 and 90 degrees, of course, if theta itself increases, then the acceleration would also increase. And that's exactly what they're talking about here. So in between bumps, it's going to be the same kind of effect, right? Because it's just a regular inclined plane between bumps. So what's going to happen to that maximum speed? It's going to once again be greater than it was in the previous case. Explain your reasoning? Well, let's make sure that we cover our facts here. We'll cover our kinematics, which in the last question here, just to mention this here, in the previous question, it really came down to the kinematics of motion. I only really mentioned distances and times to explain the velocity. I think I'm going to go necessarily, one step deeper into part C to explain not merely the kinematics of what's happening, but really the dynamics of what's happening. Like, why would a greater ramp angle lead to a greater acceleration in the first place? So let's get into this. With a larger angle of incline, theta, the dynamics is that there's a force of gravity that is pulling down, but that force of gravity can be thought to be in components. In fact, let me just kind of temporarily sketch this in up here. For an object, I'll just use the cart here, we can visualize the force of gravity as a downward force, sure, but it's often useful to think of the force of gravity as having a component. So this is a component, a force of gravity component that is essentially parallel to the ramp. That's one way I like to kind of record that, just using the parallel symbol, and another component that is perpendicular. So force of gravity perpendicular. And of course, as the angle increases, two things happen. The force of gravity parallel component itself increases, so as the angle gets bigger, this also gets bigger, but at the same time, this gets smaller. In fact, if you can imagine this angle increasing to 90 degrees, then the full-on force of gravity would be parallel to the vertical ramp, right? The force of gravity is already vertical, and none of the force of gravity would be perpendicular to that vertical surface, because the force of gravity is down. All right, so let's see if we can kind of get a little bit of that included in my explanation down below. All right, so with a larger angle of incline, there is a larger component of the force of gravity on the cart. That is directed parallel to the surface, to the bottom of the ramp. This will cause a larger acceleration for the cart. So even for equal distances between bumps, it will reach higher speeds. And of course, that was what the question was asking about, right? Will the maximum speed be greater than, less than or the same as before. So it will reach higher speeds, including, again, just to be very, very pinpoint precise here, including, because they specifically called out that maximum speed, including the max speed reached just before interacting with a bump. All right. So that should do the trick. And again, don't get hung up on the exact words that I'm using here. As long as you can convey that same essence of your understanding why this is happening and you're able to explain your choice, you should be in good shape. So I think I've answered the question fully, and I've got nothing further to say on it, so I'm going to move on to the next part. Okay, part D. Part D says, before deriving an equation for a quantity such as V average, it can be useful to come up with an equation that is intuitively expected to be true. So they're just giving you some kind of background, just general information here. That way, the derivation can be checked later to see if it makes sense physically. Okay, so that's really important, to see if it makes sense physically. So, for example, we know that as you increase the ramp angle, we expect the acceleration to be greater and the V average to be greater, just like we had talked about. That physically makes sense. All right, so they're going to now present us with a hypothetical situation. So some hypothetical student comes up with the following equation for the cart's maximum average speed. Now, notice the wording of this sentence, right? A student comes up with the following equation. That's a tip-off to me to say that whether this equation is correct or not is not certain. This student might be exactly correct. The student might be mistaken. So let's not take that equation as something that we can necessarily trust. In fact, I think that's part of the question that's coming up. So we're given this hypothetical student's equation in where C is a positive constant, and of course you can see our variables: the mass of the cart, the g value, the acceleration due to gravity, the angle of the incline, and the bump spacing d. Part 1 here says, to test the equation, the student rolls a cart down the long track with speed bumps many times in front of a motion detector, and the student varies the mass m of the cart with each trial. Okay, so this is singling out mass. Okay, so we're varying mass from one trial to the next. That's the only thing on the right side of that equation that is changing in this student's experiment. So they're varying the mass, and of course they're measuring to see what the outcome is. How does that affect the average speed? Okay, so let's just be clear here that if before I even look at the data that's below here, according to this equation, which again I'm not confident in, it may or may not be correct, but if C is constant and G, theta, and D are all constant, if M is the one and only one thing varying on the right side of this equation, then I could think that V average should be expected to be proportional to mass. Okay, now what this statement means is that assuming that all of the other variables are locked in, and I guess also assuming that they're not zero, for example, I'm definitely assuming a non-zero value, then if you mess around with the value of mass, then the value of the velocity average should be affected by that same proportion. So for example, if you, just again as an example, if you took the mass and increase it by a factor of 10, so it goes from 3 kilograms to 30 kilograms, or whatever, okay, just if you bump it up by a factor of 10, I would expect, based on this equation, for the average velocity to also get bumped up by that same factor of 10. Whatever proportion you step up the mass, this equation predicts the velocity average to be affected by that same proportion. Okay, so with that in mind, I think I know where this question is heading. So the student has performed this experiment, and the graph below is the student's plot of the data for the average velocity as a function of mass. So here we have the mass. Let's go back to a highlighter here. Here we have the mass that the student was varying. You can see that the student ran multiple trials here. So apparently the student started off with a mass of about half of a kilogram, maybe 3/4 of a kilogram, 1 whole kilogram, and so on. Okay, so there's various mass values that this student investigated. And each time they measured the corresponding, in fact, let's let's change that from a highlight to something that'll stand out a bit like this. Okay, so when they had this much mass, so roughly, I'm just going to say roughly half of a kilogram, they have this much average velocity. And again, I'm just, estimating here. If that's 1, that's 1.5, something around 1.2 or thereabouts, and so on, right? So we have multiple data points. So the question that we're asked is, are these data, like each data point here represents one piece of data, consistent with that student's equation? Well, if you recall, I was predicting that the average velocity should be proportional to mass. If you bump up the mass by any factor, I would expect the velocity average to be affected by that same proportion. Well, let's call this out. Notice, for example, and it's just one example here. Notice that in going from half of a kilogram to 1 whole kilogram, the mass doubles. Okay, so if that student's equation is correct, then we would predict that the velocity should also double, right? A factor of 2. So if the velocity in that first trial was, 1.2 or 1.3, whatever that is, then I'm expecting that doubling the mass should give me, it should, this is what I'm expecting, it should give me an average velocity of about here. In fact, I'd expect the graph, really, especially with those 2 data points in there, I can sketch it. This is what I would expect if the student's equation was correct. I would expect it to go through the origin, because if in fact, look at the equation. If the mass itself was 0 or approaching 0, then that average velocity would also approach 0. That means it really is expected to go through the origin. So this blue line here represents what I would expect it to look like. And of course, what we have from this student is something far from it. It looks approximately linear. We're kind of forgiving as for there being some uncertainty or some experimental error. It looks pretty close to linear, but this is definitely not satisfying my test for proportionality the way it should be. So with that said, let me just clear this out. I like to temporarily draw things in and then end up erasing it, I know. Are these data consistent with the student's equation? The answer to that is no, it's not. Briefly explain your reasoning. Let me just summarize what I've already been talking about, trying to be clear and concise in my written form here. The student's equation predicts the average. In fact, let's just use their symbol for it, the V average. The V average to be directly proportional to mass, M. So this would require the graph to go through the origin. In fact, by the graph, what I really mean is a line of best fit. Let me just slip that in. Line of best fit. Okay, so referring to the graph wasn't very precise, so I'll try to get that a little bit tighter in there. The line of best fit to go through the origin, and if the values for mass double, for example, V average should also double. The given graph is not consistent with these expected features. So it is not consistent. Okay, so something like that. Well, I don't know how helpful that was to say it's not consistent, so it's not consistent, but I think that I've got it well enough. I don't want to erase that and kind of redo it. I think that's fine. Okay, so moving on. Another student suggests that whether or not the data above are consistent, so we're basically saying forget all about this graph for this next part of the question. Another student suggests that whether or not the data above are consistent with the equation could be incorrect for other reasons. So the question is now saying, does the equation make physical sense? Okay, so physical sense. Well, let's remind us of what that equation exactly was here, right? Does this equation make physical sense? Now, bear in mind that we've already been thinking about this situation for a while, right? We've already answered the previous questions like part A and part B and so on. We've already made predictions such as, for example, if the ramp angle, so if theta increases, I expect the V average to also increase. Does this equation show that? Actually, yes, it does. Because again, from 0 to 90 degrees, if theta increases, the sine of theta increases. If that's the only thing being messed around with on the right side of the equation, that actually does make sense. So at least as far as having the sine theta present there, I'm actually happy with that. I mean, that does make some physical sense here. So I have no issues with sine theta. If sine theta was in the denominator, I would have issues with it, because then it would be predicting the opposite of what we've just said. But sine of theta actually looks pretty good. So no issues there. Okay, so how about the, well, we could talk about mass, I suppose. We could introduce this, but I'd rather not, because we just talked about that in the graph, and they said to, disregard the data that we just looked at. Okay, so let's maybe downplay that. Let's focus on something that is, in my opinion, an immediate deal breaker. Okay, so whereas I had no issues with the theta being where it was, I have serious issues with this distance d here. I'll remind you that d stands for the distance between the speed bumps. We've already talked about how if you increase the distance between the bumps, we would expect there to be an increase in the average speed. We've already written that up, in fact. And yet, as this equation is written, okay, this equation is predicting, in effect, the opposite of that. This equation is predicting an inverse relationship, which is to say, according to this equation, if you increase the distance and don't change any of the other things on the right side of the equation, then this equation says you should expect there to be a lesser average speed, like it's going to slow down on average. That doesn't make sense. In fact, that's the exact opposite of what we've already explained. So I think I'm now prepared to go in and answer that question about this student's equation. So, does this equation make physical sense? I'm going to say, no, it does not. Explain your reasoning? Well, let's just kind of summarize what I just said. The student's equation predicts the average speed to be inversely proportional to the distance between bumps. In other words, V average is inversely proportional to D. So that's what the equation is predicting. This is the opposite. This is the opposite of what we expect as discussed. In fact, I think I can refer to this as discussed in part. Okay, let me just kind of refer to that. In part, we were looking at the distance being varied. It was the ramp angle. I think it was, right here. It was right here. In part B is where we were talking about that distance of the bumps. If the distance increases, we're expecting a greater average speed. So, in part B, we've already talked about that. So how about if I just say, as discussed in part B, where I'll just remind us of what that conclusion was, though, where we concluded that the average is actually expected to increase with increasing distance d. So there we go. I think we've just kind of proved ourselves that that equation does not make physical sense. And by the way, it doesn't matter if it passes certain tests. It doesn't matter if it's like, well, you know, the sine of theta looks good. Who knows? The g could be fine there. The constant, like, don't single out the things that might be okay. All it takes is one deal breaker for us to say no. And you would be wasting your time if you were to elaborate and say things like, well, certain aspects of it kind of make sense and certain aspects don't. That wasn't the question, right? The question wasn't to give it a full critique and, you know, what is good about it, what's bad about it. The question was more focused than that. It was, does the equation as a whole make physical sense? No, it doesn't. So answer the question, and don't try to elaborate beyond what has been asked. That's something that I know that I repeat and say often, but the number of times that I've seen a student kind of go off on a tangent into a topic area that wasn't even asked in the question, they're wasting time and jeopardizing their credit too, because if they make a mistake or get too far astray, it can actually be penalized in certain cases. So I think that's actually the end of the question, so that wasn't too bad. Hopefully that was of some help for you. I do plan to make more of these video solutions in the coming days, so check back for more coming up.